What if your smartwatch could literally run on your sweat?
Hmm.
Or your clothing could feel the world around it, just like your own skin.
Yeah, imagine that.
Imagine devices that learn and adapt, not with rigid circuit boards, but with something more like, well, like a biological brain,
Mhm.
soft, flexible, and totally sustainable.
It sounds like sci-fi, but it's really happening. This isn't just a dream anymore. It's the electrifying frontier of iontronics.
Exactly. Today, we're plunging into an incredible world, iontronics. It's a field that could really redefine our relationship with technology.
It absolutely could. Our deep dive today is powered by a pretty groundbreaking review. It's called Iontronics, Neuromorphic Sensing and Energy Harvesting.
Right.
And it's by Yoon-gu Rho, Sang-yoon Na, Ji-yoon Kim, Yujin Chang, Sunil Lee, Min-sub Kwok, Seok-ki Jung, and Hun-hyub Ko. Published in ACS Nano just this year, 2025. It's a really comprehensive look.
Okay, so our mission today is to unpack how this revolutionary tech, which uses ions instead of electrons, how it's driving the next wave of intelligent sensing and sustainable energy.
Yeah, for everything from truly smart wearables to, advanced, almost lifelike robotics.
So what does this fundamental shift really mean for you, listening out there, and the future of tech? Let's explore.
Okay, so at its heart, Iontronics completely rethinks how electronics actually function. You know how most of our everyday gadgets, your phone, your computer, they hum with the flow of tiny electrons zipping through metal wires.
Yep, the standard way. Tiny electric highways.
That's traditional electronics. Now, Iontronics, it takes a path that's, well, far less traveled and honestly far more organic.
Oh, yeah.
Instead of electrons, it uses ions.
Yeah.
Those are just atoms or molecules with a positive or negative charge, and their movement carries signals and energy.
Ah, okay. So think of it like maybe the difference between a standard electric current in a wire, that's electrons, and the way our own nervous system works, which uses ions moving in and out of cells.
Exactly, you nailed it. Our brains are fundamentally iontronic devices. Seriously. Your thoughts, your feelings, every muscle movement, it's all driven by ions moving across membranes. And mimicking biology like this, that's a monumental advantage for creating tech that feels less like a machine and more like, well, part of us.
And this is where it gets really interesting, right? Because our bodies run on ions, these iontronic devices can mimic biological systems much more closely.
Right.
And that's not just a neat trick. It's absolutely crucial for what they call neuromorphic sensing, meaning systems that can literally learn and remember, kind of like a brain does.
It's about building intelligence that's more intuitive, not just rigidly programmed step by step.
So beyond that really profound biological connection, what about the materials themselves? Are there practical advantages?
Oh, definitely. Huge ones. Think about this. Ions can act as plasticizers within polymer materials.
Plasticizers, meaning they make things more flexible.
Exactly. They can make these materials incredibly flexible, stretchable, even soft, like really soft.
That's a massive leap from the rigid, brittle circuit boards we're all used to. This flexibility isn't just about making, bendy phones. It sounds like it could fundamentally blur the line between technology and us.
It really could. Enabling devices to become truly invisible or feel like a second skin. It just redefines what wearable can even mean.
And the review you mentioned, Rowe and colleagues, it highlights that these devices are also designed for low-power operation, so they're energy efficient too.
Astonishingly so. They're built for high sensitivity but low power draw.
Okay, so let's look at iontronics in action. First up, neuromorphic sensing, how these smart devices are learning to think and feel a bit like us.
Right. So our brains operate through billions of connections called synapses. That's where neurons talk to each other, allowing us to learn, form short-term memories, and eventually, long-term ones.
Okay.
And researchers are now engineering iontronic devices to replicate these very synaptic behaviors. They do it by carefully controlling how ions move within the material.
So they're building artificial synapses.
Essentially, yes, which allows for creating artificial sensory systems that can process information with a kind of brain-like capacity.
Okay, give us an example, like artificial touch, smart skin.
Perfect example. Imagine a prosthetic hand that can truly feel the texture and pressure of what it touches. Or maybe a robot with skin as sensitive as yours.
That would be incredible.
Well, iontronic systems are being developed to mimic our human mechanoreceptors, those specialized cells in our skin, like Merkel cells for steady pressure and Meissner's corpuscles for dynamic touch, like vibrations or a quick tap.
So they can tell the difference.
That's the goal. And there's a fantastic example from Huinen and colleagues, published in the journal Device in 2023. They developed self-powered pressure sensors that could differentiate between dynamic, fast-adapting pressure and static, slow-adapting pressure.
It's like our skin does. Wow.
Exactly like our skin.
So this means future robots could, I don't know, distinguish between a soft touch and a firm grip. Or tell if something is squishy or hard, with almost human-like discernment.
That's precisely the direction this is heading. It's a level of nuance for artificial systems that was, frankly, pure science fiction not long ago.
Okay, touch is one thing. What about hearing? Are they making artificial ears too?
It's a bit less explored, but yes, researchers are looking into artificial auditory systems. They're often combining iontronics with something called triboelectric nanogenerators, or TEMs.
Okay, TNs, what do they do?
They help convert sound waves into electrical signals. Those signals then trigger the ion movement needed for processing the sound information. For instance, he and colleagues, writing in Nature Communications in 2023, they demonstrated a system that could actually detect the direction of sound by mimicking the tiny time differences in how sound reaches our two ears. It's quite clever.
That is clever. But you said it's less explored. Are there big challenges?
Yeah, there's a key one. It comes down to speed. The fundamental issue is the slower mobility of ions compared to electrons.
Ah, okay. Ions are just bigger and heavier. They move slower.
Pretty much. And this currently limits their ability to process high-frequency sounds. You know, the range humans hear, roughly 20 hertz to 20 kilohertz, as quickly as conventional electronic systems can.
So a bottleneck based on physics. Are they working on ways around that?
Oh, absolutely. Material science, device architecture, people are trying different things. It's a very active area of research.
Okay, so we have touch, we have hearing.
Yeah.
What about sight? Could iontronics lead to, say, bionic eyes?
That's definitely a major goal. Researchers are using light-sensitive materials, often integrated with these ion-rich electrolyte layers, to create artificial retinas.
Artificial retinas.
And these devices can even mimic something called synaptic persistence.
Which is like an afterimage, a memory of the light.
Exactly. That lingering signal after the light stimulus is gone. For example, Kim and colleagues, again in Nature Communications, this time in 2025, they developed an artificial synapse using something called metal organic frameworks, or MOFs.
MOFs, what are they good for?
They're incredibly porous structures, really good for controlling ion movement precisely, and they use these MOFs to filter visual information, replicating both short-term and long-term synaptic behavior, like memory.
Okay, that's impressive. Any other examples?
Yeah, another team, Luo and colleagues, writing in Springer Nature in 2024, they designed a stretchable, self-powered photosynaptic retina. It used something called inodule heterojunctions.
Stretchable and self-powered.
Yep. And it could respond to light across a really broad spectrum, from ultraviolet all the way to near infrared.
Seeing that wide range, and with memory, that's genuinely amazing. But I'm guessing the speed issue crops up here too, like with hearing.
You got it. Despite these incredible advances, the responsiveness, the speed of iontronic visual sensors is still generally lower than traditional semiconductor-based systems. Again, it comes back to that slower ion diffusion. Light is just incredibly fast.
Right, makes sense. What about the other senses, smell and taste? Is Iontronics tackling those?
They are, yeah. Researchers are working on mimicking olfactory, that's smell and gustatory taste perception. They're trying things like ion-selective membranes or specific molecular detection arrays, trying to replicate the chemical sensing our bodies do.
But that sounds complex.
It is, and it's still early days with some significant challenges. For instance, many artificial noses, the olfactory systems, currently need an external voltage boost, which kind of defeats the purpose of low power, right?
Yeah, it limits the efficiency.
And for taste sensors, a challenge highlighted by Yang and colleagues back in 2020 in the Chemical Engineering Journal is that repeated use can lead to leftover ions accumulating in the device.
Gunking up the works.
Kind of, yeah. It degrades the sensitivity over time. So getting that selectivity and durability right is tough.
Okay, so that's the sensing side, mimicking biology. Let's shift gears now, because all these amazing smart devices, they need energy.
They absolutely do.
And this brings us to the other huge area for Iontronics, sustainable energy harvesting. We all know there's a massive global need to reduce our reliance on fossil fuels.
Urgently.
And Iontronics seems to offer a really promising strategy for localized sustainable power, especially for smaller devices, right?
Exactly. And what's truly revolutionary here, potentially, is that your own body could be the power plant.
My body.
Iontronics can harvest what we usually think of as waste energy from body fluids like sweat, from your body heat, even just from you moving around.
Okay, that is a game changer for self-powered wearables. No more charging my watch, maybe?
That's the dream. Imagine your smartwatch powering itself from your morning run or even just sitting there on your wrist using your heat.
So how do they actually do that? Let's start with the sweat power.
Okay, one key area there is hydrovoltaic energy generators, or HEGs. These basically harvest power from water and moisture.
From sweat or even just humidity in the air?
Both. They can use the ions naturally present in your sweat or even just moisture from the environment to generate electricity. They essentially create an ion gradient as the water moves or evaporates through the device material.
So flow-driven generators using sweat. That's ingenious.
An example?
Any examples?
Oh, yeah. For instance, Shen and colleagues, writing in Wiley VCH back in 2018, they reported high power density HEGs using stacked titanium dioxide, that's TiO2 nanowires.
Nanowires, right?
And Xu and colleagues in Springer Nature in 2017 showed porous carbon black sheets generating sustained voltages just from evaporation-induced water flow.
So just water evaporating can make electricity.
In these systems, yes.
Yeah.
And more recently, Zhao and colleagues, publishing in the American Chemical Society in 2023, they developed these things called organohydrogels.
Organohydrogels.
Yeah, they basically provide their own self-sufficient water supply within the device, which means they could generate power for over 15 days continuously.
15 days, just passively. That's incredible.
It really is. Imagine that kind of sustained ambient energy.
Okay, so that's flow and evaporation. What about just individual water droplets, like rain or even just a splash?
Yep, they're working on that too. Kong and colleagues in Advanced Energy Materials in 2022 significantly improved the output power by using microstructured graphene layers to interact with droplets.
Graphene, right, that wonder material.
But get this is the real wow fact here. Leaks and colleagues, also in Advanced Energy Materials, just last year, 2023, they achieved an ultra-high output voltage of 1,200 volts.
1,200 volts from what?
From falling tap water.
Yeah.
Just regular tap water dripping onto their optimized device.
No way.
Yes way. By really optimizing the contact dynamics and the capacitance of their system, that's the highest voltage reported to date from that kind of hydrovoltaic effect.
Wow. 1,200 volts from tap water. That is genuinely remarkable. It really speaks to the potential. But what's holding these HEs back from being everywhere right now?
Well, a couple of key things. First, maintaining a continuous water supply for consistent output. That can limit portability, if it relies on ambient humidity, what happens in dry conditions.
Right.
And second, long-term durability is still a concern. Water evaporation, potential leakage. These can degrade performance over time. So robust encapsulation, sealing the device properly, is really critical.
Okay, makes sense. So we can use sweat and water?
Right.
Can we use our body heat too? We're all basically walking radiators.
We are. And yes, that's where ionic thermoelectric generators, or ITE generators, come in.
ITE.
They're designed specifically to convert low-grade heat, like your body heat, which is usually around, 32 to 35 degrees Celsius, into electrical energy.
So not big temperature differences, just that little bit of warmth. How?
It relies on something called the Soret effect. Basically, a temperature difference across the material actively drives the ions to migrate from the hot side to the cold side. That movement of charge is your electric current. It's also called thermodiffusion.
Okay, the Soret effect. And how efficient are these compared to existing thermoelectric tech?
This is where they really shine. Iontronic ITEs have significantly higher Seebeck coefficients.
Seebeck coefficient. That measures how much voltage you get per degree of temperature difference.
Exactly. And these ionic systems have much higher Seebeck coefficients than conventional electronic thermoelectric devices, especially at small temperature differences. This makes them way more efficient at harvesting low-grade heat, which is usually just wasted.
That's huge.
Yeah.
Because there's low-grade heat everywhere.
Absolutely. Chen and colleagues, for example, writing in the American Association for the Advancement of Science in 2021, developed an ionic hydrogel that generated a giant negative thermopower, really demonstrating this potential.
Giant thermopower. Sounds good. But efficient doesn't always mean practical. Are there any trade-offs?
There are. One important point is that these thermodiffusion-based ITEs, the current they generate, tends to diminish over time. It acts more like a capacitor charging up and then discharging, rather than providing truly continuous, steady power indefinitely from a constant temperature difference.
Okay. So it's not like a battery that just keeps going.
Not exactly in the same way, no. Also, maintaining mechanical durability while achieving that high thermopower is still a major hurdle.
Hmm.
You need materials that are good thermally and robust mechanically.
Right, the flexibility challenge again. Okay, so we've got sweat, we've got heat. What about just moving? Can we power things by walking or flexing or stretching?
Absolutely. Enter mechanoionic generator.
Mechanoionic. Makes sense.
There are two main types here. First, you have piezoionic systems.
Piezo. Like
Yeah.
piezoelectric materials that generate voltage when squeezed.
Similar concept, but here it's the mechanical stress deforming a polymer, and that deformation drives ion movement, which generates the electricity. For instance, Zhu and colleagues, writing this year, 2024, in Advanced Materials developed piezoionic elastomers.
Stretchy polymers that make electricity when you deform them.
Exactly, and they designed them to concentrate the mechanical pressure, which significantly increased the voltage output.
Cool. What's the second type?
Those are triboiontronic generators, sometimes called TINGs.
Tings. Okay, triboelectric refers to static electricity from friction or contact, right?
Right. TINGs convert mechanical energy from contact and separation into electricity, like traditional TINGs do. But the key difference is that mobile ions within the iontronic material fundamentally enhance the charge generation process.
Ah, so the ions give it a boost.
Precisely. Poot and colleagues, back in 2017 in Science Advances, created an ultra-stretchable, transparent triboelectric nanogenerator. It used a hydrogel elastomer structure, and they showed it actually performed better when it was stretched.
Better when stretched. That's interesting.
And Lee and colleagues, writing in Elsevier Ltd. In 2021, they explain the physics of how these mobile ions are really key to boosting performance compared to traditional tangs, helping them achieve a higher power density.
This is all incredibly exciting. So many different ways to tap into energy that's just all around us or part of us. But I imagine these energy harvesting techs still face some big challenges before they're, in our phones or powering sensors everywhere.
They certainly do, yes. A major one for the mechanoional generators, for instance, is still relatively low power output.
Not enough juice yet.
Often, yeah. We're talking maybe less than tens of microwatts per square centimeter in many cases, which is great for tiny, ultra-low power sensors, but often not enough to directly power more complex electronics we use daily, like a display or a transmitter.
Okay.
Plus, internal resistance within the devices, and the fact that many of these soft materials are viscoelastic, meaning they deform slowly and dissipate energy, that also limits the overall efficiency.
So it sounds like maybe combining these different approaches might be the way forward. Don't rely on just sweat or just heat or just movement, but maybe all of them.
Exactly. That's a huge area of focus now. Synergetic approaches, combining different energy harvesting mechanisms.
Like thermal and moisture
Yeah.
together.
Precisely. To overcome the limitations of relying on just one source and hopefully achieve more stable, continuous power. For example, Yang and colleagues just last year in Advanced Science, they integrated a thermodiffusion ITE generator and a moisture electric generator into one device.
What was the benefit?
They could efficiently utilize waste steam, capturing both the heat energy and the moisture energy simultaneously. It's about getting more bang for your buck from whatever ambient energy is available.
So what could these combined systems power in the real world? Maybe soon.
Well, they could lead to truly self-powered health monitoring devices. Imagine, say, a face mask that detects your breathing frequency and maybe alerts you to changes, but never needs a battery charge.
Wow.
Or maybe wearable keypads for real-time control of other devices, like Raman and colleagues demonstrated in Wiley VCH in 2023. We're really talking about technology that could just fade into the background, always on, always sensing, always ready, powered by the environment.
Okay, so we've covered a lot of ground. Amazing advancements, from smart skin to sweat power. But let's zoom out again. What are the big picture challenges that need to be cracked for widespread adoption of these iontronic energy harvesters?
Right, the hurdles. There are a few key ones that researchers are really focused on. Firstly, as we've touched on, low power density is still a primary issue for many applications.
The speed limit of ions again?
Fundamentally, yes. Ion transport is just significantly slower than electron transport in wires. This generally leads to lower power output compared to conventional batteries or power sources of the same size. Often, you'd need to connect multiple devices together in series or parallel to get enough power, which increases the overall system size and complexity.
Okay, so power density is number one. What else?
Secondly, stability and long-term durability. This is crucial. Many of these systems rely on electrolytes that contain water or quasi-solid gels.
And water evaporates, or things can leak.
Exactly. Over time, that can degrade performance significantly. So, developing robust, long-lasting encapsulation methods, ways to perfectly seal these devices from the environment while still allowing them to function, that's absolutely critical for practical everyday use.
Right, you need them to last for years, not days. What about integrating them with the electronics they're supposed to power?
Yeah, integration complexity is another factor. While the goal is self-power, actually connecting these iontronic harvesters seamlessly with existing silicon electronics often requires extra bits of circuitry.
Like what?
Well, many harvesters produce alternating current, or AC, while most electronics run on direct current, DC. So you need rectifier circuits to convert AC to DC, maybe voltage regulators. It
Mhm.
adds complexity and potential points of failure to the overall system.
Okay. And finally, I guess cost. Making them cheap enough.
Absolutely. Cost and scalability, some of the advanced materials like specific MOFs or complex polymer structures and the fabrication processes needed to make these tiny, intricate devices, they can still be expensive or difficult to scale up for true mass production. Getting the cost down while maintaining performance is always a key challenge for new technologies.
This has been a truly fascinating deep dive, really eye-opening. So let's try and tie it all together for you, our listener. What are the key takeaways from this incredible journey into Iontronics?
Okay, takeaway number one. Iontronics are truly bio-inspired and flexible. They harness the movement of ions just like our bodies do to create devices that are flexible, stretchable, and incredibly low power.
Yeah.
And they can mimic the sophisticated sensing and even computing abilities of biological systems. It's really technology designed with life and like life in mind.
Okay, great first point. Second takeaway.
Second, they're paving the way for sustainable power, basically everywhere. This tech offers really innovative ways to harvest energy from sources all around us, our own bodies, our sweat, heat, movement, and the general environment,
Right.
which opens the door for truly self-powered wearables, smart sensors, autonomous systems that might never need plugging in or a battery change.
Fantastic. And the third point.
And third, while the future for Iontronics looks incredibly bright, there's still significant work to be done. We talked about the challenges improving power density, ensuring that long-term stability and durability, and figuring out how to scale up production affordably. These are key areas for ongoing research, driving us closer to that bio-integrated future.
Absolutely. Iontronics really do feel like a transformative leap, don't they? Properly bridging that gap between biology and electronics.
This feels like it, yeah.
They promise a future where our devices aren't just smart in a programmed way, but are also intrinsically adaptive, super energy efficient, and so seamlessly integrated with our lives and the world. They might just disappear into the background.
Become part of the fabric of things, literally sometimes.
Right. So here's a final thought to leave you with. As we move towards this potential future, one powered by the very fluids and motions of our existence, what truly unimaginable applications will emerge when technology can genuinely feel and maybe even think with the kind of natural intelligence we see in life itself?